All right. Up until this point, we have been talking about singly reinforced concrete beams. Singly reinforced means there's only reinforcement on one end, side, whatever you want to call it, of the cross section. And that is used for tensile reinforcement, right? Because concrete's terrible in tension, so we're not even going to pretend that it has strength. And so the steel is there specifically for providing tensile strength. So this is singly reinforced. Let me write that smaller. Singly reinforced. All right, only on one side. Now we're going to talk about doubly reinforced. Where we have reinforcement on the top as well as the bottom, presuming we're under positive, we're relying on our cross section for positive bending. So if we look at the strain, right, we draw our ever familiar linear strain profile where our strain at the top, the extreme compression fibers is equal to the ultimate strain in concrete, ECU, 0.003. We have strain in our steel, our tensile steel. This is called the tensile steel, right? We have strain in our tensile steel. Hopefully it's yielded, meaning we have, and it's yielded so much that it's tensile controlled, right? And the determination, we determine our strain values based off of the geometry here, where we have the depth to the centroid of the steel, of the tensile steel, D, and then the depth to the neutral axis, C. This strain profile results in compressive stress in the concrete, which we've estimated using the Whitney stress block. It has a value, a magnitude of 0.85 F prime C, and it happens over a height A, which is equal to beta 1 times C. At the other end, we have tensile stress in our steel, Fs. If it's yielded, if our strain is beyond yield strain, it'd be Fy, but it's Fs generically. And then we resolve those into forces, which is C sub C, the compression force in our concrete, and T, which is the tensile force related to our steel. Now in a doubly reinforced section, we have tensile steel in the bottom and compression steel in the top. It's called compression steel because it's in the compression portion of the strain profile and the stresses. All right, if we draw our strain, the compression steel, the centroid of it, is in the compression portion of my strain profile. I'm still going to assume ECU there for my extreme compression fiber and my concrete. The strain value down here, ES, but now we also have ES prime. When we start talking about anything in the compression portion of the cross section, we're going to add a prime to it. Prime is, let me make that a different color. Prime symbol right. Denotes compression steel. Right, so I have a prime for my strain, ES prime, that's the strain in my compression steel. I'm gonna stop right here for now. Well, no, I'm gonna keep going. As a result, let's see, I have right. Trying to make sure that this looks shorter. You'll figure out why, but I have the stress from my Whitney stress block in my concrete with a value of 0.85 F prime C. I have the stress in my tension steel with a value Fs. But if I have strained my compression steel, applying a strain means there's stress in it, right? Except it's not in tension, it's a compression stress. So that is a value Fs prime. If I go back and talk about the dimensions that I care about, I still have D, the distance from my extreme compression fiber to the centroid of my tensile reinforcement. Now I have D prime, which is the value of my distance from my extreme compression fiber to the centroid of my compression reinforcement. And I have a distance to the neutral axis C, that Whitney stress block here. A is equal to beta 1 times C. I'm going to resolve these stresses into forces. I have my concrete compression force, C sub C, but I also have, if we just want to make sure, like we're going to follow this line, right? I also have a compression force in my steel that happens at the centroid of the compression steel at D prime. And I finally have the tension force in my tensile steel. So let's define some stuff here. D prime. D prime is the distance from my extreme compression fiber to the centroid of my compression reinforcement. Which one is a larger value, D or D prime? D, right? D is the distance from the extreme compression fiber to the centroid of my tensile reinforcement. D prime is from the extreme compression fiber to the centroid of my compression reinforcement. D, tensile reinforcement, D prime, compression reinforcement. They're both from the same point, assuming that's where I'm going to have my compression at the top for positive bending. But obviously D prime would be smaller because it's in the compression portion of the of the cross section. ES prime, that's the strain in at the centroid of the compression. Right. ES is the strain at the centroid of the tensile reinforcement. ES prime is the strain at the centroid of the compression reinforcement. Remember, this happens at the centroid, so if there's like 2 layers of one of the types of reinforcement, the centroid is between those 2 layers. In this case, we only have 1 layer of each type, so it's at the centroid of those bars. And all the strains are related because I'm assuming on a linear relationship, a linear profile, right? So they're all related by geometry based off of the assumption of ECU is equal, the extreme compression fiber is equal to ECU, which is 0.003. That's the ultimate strain of concrete. I know these values, D prime and D, based on the geometry. C, I do have to calculate, and ES will be based off of that with my assumptions of equilibrium. What's other value? Let's see, we have the other value I was going to write was, let's see, oops. Fs prime, that's the stress. Reinforcement. And it is based on the strain at the centroid. So Fs prime is equal to the modulus of elasticity of steel times the strain and the compression reinforcement. And let's see, we have Cs, which is the we're going to resolve that stress into a force. Is equal to Fs prime times As prime. I guess I didn't say what that was, right? As prime area. This is As prime, this is As, the tension steel. You'd say they're all number 9s, so they're an inch and a square inch. So the top compression steel, As prime, if it was 2 number 9s, would be 2 square inches. The bottom tensile steel, if it was 3 number 9s, it'd be 3 times 1, so 3 square inches. So this is just starting to get into the mechanics of how we analyze a section with compression reinforcement. So maybe we should have started here, but why might we want compression reinforcement? Well, I want you to look at this chart here where we have 2 different three different we're looking at deflection, midspan deflection over time. So this would be like essentially creep, right? For a sustained load, how much additional deflection if I keep my load on there? And this is measured in days, up to 2 years. And it's based off of 3 different reinforcement ratios. If you recall, reinforcement ratio for tensile reinforcement is equal to the area of steel over the width times my depth to the centroid, right? My beam width times the depth, which is basically your effective area of concrete. So, conversely, my compression reinforcement ratio, rho prime, is just the area of steel prime over that effective area, B times D. It's not D prime, because what they're talking about is this is my effective area of concrete. Anything below that might as well not exist. It's just there for the ride. It's there to act as cover for my reinforcement. Make that D look prettier. So this first line right here is no compression reinforcement. P prime is 0, rho prime is 0. Down right here, the bottom one, rho prime equals rho, which means, if you look at these two, if rho prime equals rho, that means your area of tension reinforcement is equal to your area of compression reinforcement. If you look at this middle one, rho prime is half of a regular rho, so you have half as much tension reinforcement in your compression reinforcement. Right? If you have 4 bars in the bottom, you have 2 bars in the top, assuming they're the same size bars. So what does this tell you? What would be the effect of having compression reinforcement? You decrease deflections for sustained loads, right? If you have no area of compression reinforcement, you have like 5.5 inches of deflection. If you have equal, you'd only have like 3 inches of deflection. Over like the span of, a couple years. So, one reason for compression reinforcement is you reduce sustained load deflections. Another really so that's an actual like benefit, right? Another less obvious benefit in terms of like the engineering part of it versus fabrication is putting something up there in the corner eases fabrication for adding stirrups, right? There's something for them to anchor to. I'm talking about if I put a hoop right there. If there was nothing there to hold those in place, they'll be like flapping in the breeze. So it's partially just there to make it easier to build stuff. Constructability, that's the word. I'm gonna skip the next two reasons because I'm gonna come back to it. Because I want to do some math to prove it. So, I'm gonna look at how I figure out the nominal strength of a doubly reinforced section, right? So, let's see. I'm gonna draw my little strain profile. You should be a pro at these right now, right? The strain in my extreme compression fiber is ECU. I've got this. I should add a line there. Right. I've got this. Compression steel. It's gonna have, pardon me, a strain value ES prime, a strain value down here, strain in my compression, in my tensile reinforcement, right? Draw all my lovely geometry, D prime, D, the depth of my neutronics is C. And now let's look at the resulting stress, right? I've got the stress in my compression block, the Whitney stress block, with a magnitude of 0.85 F prime C. I've got some stress in my reinforcing steel, in my compression steel, sorry, equal to Fs prime. It's based off of that ES prime. It's a compression force. And I've got stress in my tensile reinforcement. This value is A, which is equal to beta 1. Beta 1 going to resolve those stresses into my compression force in my concrete, which is equal to 0.85 F prime C AB, right? If this, assuming I have my little lovely rectangular cross section with a width B, I have compression steel force CS, which is equal to Fs prime times As prime. That's the stress in my compression steel and the area of my compression steel. At the bottom, I have the tension force, which is Fs As. That's the stress in my tension steel and the area of my tension steel. This C sub S happens at D prime, which is the centroid of the compression reinforcement. Make that a little bit closer to its buddy. And the centroid of my compression concrete force, or of the stress, which is where the concrete force acts, is at A over 2. So I'm going to start with my usual, let me give you a minute to make sure you have all that down. So I'm going to start with my usual assumption, right? Assume that my tension reinforcement has yielded. If I assume that my strain in my tensile reinforcement is greater than or equal to the yield strain, then the stress is equal to the yield stress. However, the strain in my tension, or I'm sorry, in my compression reinforcement is less than my yield strain. It has not yielded. So let's do equilibrium of my forces, right? Before I just set C sub C equal to T. Now I got this C sub S in there. C sub C plus C sub S is equal to my tension. So I'm going to start over here. C sub C. All right. 0.85 F prime C AB. However, I have to subtract out my area of my compression steel. Because my area of my concrete in compression is not just AB, it's AB minus the area of compression steel. Minus FS sorry. Subtract out AS prime. If I want to look at that visually, right? If my area in compression is right, A times B, but I got these two little bars that aren't concrete, they're steel. So area of concrete actually in compression, right? Is A times B minus AS prime. Just like when we were doing the triangular section, my area of concrete, if I was a triangle, right, was that, and I had to calculate the area. My area now, it's a rectangle, A times B, but I have to subtract out that compression reinforcement. So that is what this is doing, AB minus AS prime. So my compression steel force, FS prime, AS prime. It's going to equal my tension, AS, F, Y. I could have put that up here. FY, AS, based off of my assumption, right? Gonna rearrange this a little bit, so I put 0.85 F prime C A B plus AS prime times FS prime minus 0.85 F prime C. All I did was multiply, where's my mouse? Multiply this out, right? 0.85 F prime C times minus AS So I have minus 0.85 F prime C AS prime plus FS prime AS prime, and then factor out the AS prime. So if you're taking a little note there, you'll say this is concrete compression force. C sub C. And this is your corrected steel compression force CS. Just a little bit of rearranging, and there's a reason for it. There's a reason that we're doing this. It's because if I look at my forces, if I keep my C sub C as 0.85 F prime C AB, then it gets to act at the centroid of that stress. If I kept it with AB minus AS prime, then the centroid of that area, right? I'm talking about, oh, that's terrible. I'm gonna draw this. You know what? Don't draw this. Erase it if you have, or just ignore it. What this is saying is, if I look at the cross section here, this might actually be a better little drawing. This has a dimension A, this has a dimension B, C sub C equals 0.85, that's the magnitude of my stress. 0.85 F prime C, which happens over an area AB. this is the magnitude of my stress here is Fs prime minus 0.85 F prime C times that area of steel. Right. This is this is so I'm placing my correction where I subtract the Fs prime, or sorry, subtract the 0.85 F prime C area, right? This little correction right here. Place the correction at the same height as AS prime, which would be D prime. So that C sub C is placed at A over 2 and C sub S is placed at D prime. Makes calculating NN much easier. So you guys write that down and then I'll show you if you haven't figured out what I mean by this. If I didn't do this, if I stuck with what I'd done before, where I had my C sub C, right, 0.85 F prime C AB minus AS prime plus, right, if I did that, well, my area would look like this. Now I would like you to find, which one would you rather find the centroid of, right? The top one. Here's a lovely rectangle, A times B, or A times B, oopsies, minus AS prime. Which one would you rather find the centroid of? A nice little rectangle or a rectangle with two holes in it? Doesn't really matter to my CS calculation. Alright, that still happens here. Now I just have a different value of my stress. Can't even spell the word harder. You need to find the centroids in order to find the moment arms, to find the nominal capacity. So that is why we do that little correction. And 10 minutes on why we rearranged something. So, I wanted to talk about this. If I have steel in there, let's look at this. Earlier, all I had was C sub C is equal to T. Now I have this additional compression force from my steel. If I put more stuff on the left side of this equation of equilibrium, right? If C sub S is greater than 0, if I have compression force in there, what's going to happen to this force if this is still equal to ASFY? This is going to go down, right? I don't need as much compression strength from my concrete because I got some steel in there. Right? It just looks so pretty. I don't want to add any comments, so let's, right? Due to additional compression force from compression reinforcement CS less compression force is required concrete. This would be compared to a singly reinforced section, right? If my T, oh, give me a minute. If my T, my tension force, my area of reinforcement steel times, we're assuming it's yielded, so the yield stress, that's not going to change. If I push in some, if I include compression steel, this T doesn't change, so compared to a singly reinforced section, my C sub C has to go down to account for this additional force from my compression reinforcement. If my C sub C goes down, C sub C is based on the depth of that stress block A. I don't need as much of my concrete to be in compression, right? Depth of stress block. A decreases, and A is directly related to C. That's my neutral axis. I need less force, need less strength essentially, less compressive strength for my concrete because I added this steel in there. So that means I need less area of my concrete in compression. So I've decreased the depth of my stress block, A, and the depth of my neutral axis, C, because they're related. So if I go back to this guy, I'm gonna start, okay, so I have a singly reinforced and a doubly reinforced. I'm gonna add singly reinforced a singly reinforced, I'm gonna add a little SR there, and doubly reinforced. Make those big letters. A, C, singly reinforced, A, singly reinforced, beta 1, C, singly reinforced. I thought I was going to add more, but that's okay. I'm going to make this C doubly reinforced, A doubly reinforced. All I did was just add SR and DR to my A's and my C's. Top one is SR, singly reinforced, only has tensile reinforcement. Bottom, doubly reinforced, DR. So I just said that I need less for a doubly reinforced. I need less stress block depth, right? A is less for a doubly reinforced versus a singly reinforced. And because they're related, the C is less. That means less concrete in compression. So what happens if, and I tried to draw it here, what happens? So my depth by neutral axis for singly reinforced is higher than my doubly reinforced depth by neutral axis. As a result, you can kind of tell if I have a higher, let me see here. If we compare those, right? Which one has a higher strain in my tensile strain? My tensile reinforcement. Right? Because I have a shallower, right? If CDR is less than CSR, then I'm gonna have a strain profile, right? It would basically be like, you can make it super obvious, right? It'd be like, I don't know that. Right? That's not what I want to do at all. CSR, CDR, right? That's the strain profile for singly reinforced. I'm sorry, doubly reinforced. Like that, right? They have to have the same value up here, but if they cross at different spots, Look at that picture if you need to for a second. If you have smaller neutral axis, because you don't need as much in compression, then my doubly reinforced strain profile, that blue one, is going to result in higher tensile strain and tensile reinforcement. Alright. This is Alright, this is the strain and my tensile reinforcement for singly reinforced. And that is the value of my strain for my doubly reinforced. Obviously, you add in compression reinforcement, you increase the tensile strain in your tensile reinforcement. Because the compression reinforcement means less of your concrete has to be in compression. So you're decreasing the stress block, you're decreasing the area of concrete in compression, and therefore decreasing that depth to neutral axis, resulting in higher tensile strains in the reinforcement. So what it comes down to is if you add in tensile reinforcement, if you add compression reinforcement, you're going to increase the tensile strain in your tensile reinforcement, which means it's more likely to yield, right? Increase that strain, you're making sure you're yielding, and hopefully going to a tension controlled section. That is what all that explanation was about. So, reason for compression reinforcement: reduce load. You reduce the deflections for your sustained load, makes it easier to construct. Also, you get to increase your ductility. As depth of compression block decreases. All right, that's your A. As your A decreases, strain in tensile reinforcement increases. Go back and look at those drawings to maybe understand how we got there. Basically, your steel, your compression steel, is supplementing your concrete compression, so you don't need as much of your concrete to be in compression. Decrease that neutral axis, increases the strain in your tensile reinforcement, increases the likelihood of a ductile failure, which is the next thing. hopefully that means you can change your mode of failure from compression controlled to tension controlled. That's what that whole explanation was all about, right? If you find that you're not reaching yield, or maybe you're in that transition in your fee factor, and you want to switch from compression controlled or maybe tension, or I'm sorry, maybe transition to tension controlled, shove some compression steel in there, see what happens. Or include it in your calculation instead of ignoring it. So we were talking about how to calculate the nominal strength of your doubly reinforced section. We just said we found our C sub C, which was 0.85 F prime AB, our corrected steel compression force. There we go. AS prime F times FS prime minus 0.85 F prime C. We did that so that we can make this calculation a lot easier. It's easier to find the centroid of a rectangle than a rectangle with two holes in it. So now, looking at our section, okay, we got our forces. Right, we got C sub C and C sub S, and our tension force T. If we look at where those forces act, my corrected C sub S acts at D prime. C sub C still acts at A over 2 because I did a little finagling there. The distance from the top here down to the centroid of my tension steel is D. So let's see. Now I'm going to take my moment about T. Before it was just, before I took it about C sub C, because there was less numbers in there. Now, since C sub S and C sub C are close together, let's take our moment about T. So, Mn is equal to C sub C. The moment arm is D, right? This distance from here to here is D minus A over 2. So C sub C times D minus A over 2. And the distance for C sub S is D minus D prime, right? Just subtract out the little D prime. Mn is equal to C sub C, which is 0.85, F prime C AB, D minus A over 2 plus C sub S, which is AS prime, FS prime minus that 0.85, F prime C times D minus D prime. If I go to my equilibrium equation, my unknowns are, I don't know A, I don't know Fs prime. I get 0.85 F prime C A B plus AS prime that's my C sub C, and my corrected C sub S is equal to AS FY. Unknown, what do I not know? Let's see, 0.85 F prime C, okay, I know F prime C. I don't know A. I don't know that depth. B, okay, I know the width of my B. AS prime, yep, I know how much compression steel I have. FS prime, I don't know. FS prime. 0.85 F prime C, yep, I know that. I know my area of seal for my tension side, AS, and I know my yield stress. So, oh, I have two unknowns. Before, the only unknown, if I didn't include my compression steel, right, FS prime, get that out of there, I could just use equilibrium to solve for A. Now, I don't have that luxury. So, I use my strain profile. Right? E sub S prime ECU. Gonna use this right here, right? Gonna use similar triangles. This distance right here, C minus D prime. So E sub s prime over C minus D prime, right? Horizontal over vertical is equal to ECU, that's my horizontal, over my vertical distance, C. This horizontal value, ES prime, over the vertical value, C minus D prime, is equal to a larger triangle with the horizontal value ECU and the vertical value C. It all comes back to these, right? E sub s prime over C minus D prime, ECU over C. All comes back to equilibrium and the strain profile. Now my unknown variables from my strain profile are C and E sub s prime, the strain in my compression reinforcement. So it looks like I have 4 unknowns, but obviously they're related, right? Right, A is equal to beta 1C. My stress is equal to the modulus times the strain. So I have 2 equations, 2 unknowns. My equations being equilibrium and my strain profile, my unknowns being A and stress, or C and the strain. So if you followed along to the example from the other day, you know that I could just solve for one of these. Like in the strain profile, I could solve for ES prime, put it into the equilibrium equation, you'd end up with a quadratic equation. Solve using the quadratic formula. Or you could do an iterative process. Iterate. Which is where you guess a value, go back and check it. If it doesn't work, adjust your value, go back and check it. So steps, this is the iterative method if you aren't so excited about doing the quadratic formula. Right, we're going to assume that our tensile, right? Tensile reinforcement has yielded, right? We're going to select a value for C. That's my depth to my neutral axis. Use that to estimate a value of my strain in my compression steel. Use that to calculate stress related to that strain as long as it's less than the yield stress. Use that to calculate my corrected force associated with my compression steel. Right, this is my strain in my compression steel. This is my stress in my compression steel. This is my force in my compression steel. God, that looks terrible. Force in my compression steel. Calculate concrete associated with that C that you just did, right? Now we're using beta 1 times C instead of A. All right, this is just A equals beta 1C. I have this never changes. Then I say is the two compression forces, C sub C and C sub S, if I add them together, are they equal to T? If yes, congratulations, you're a really good guesser and everything's right. If no, if my tension force is less, then I need to decrease my amount of concrete in compression, so decrease C. If my tension steel, or if the force in my tension steel is greater, because remember this T isn't going to change. Really just what you're changing are these two values. I'm going to increase my C. I need to increase how much of my concrete is in compression, and as a result that would increase the strain in my steel, my compression steel, which would increase the force in it. Once you get down to a reasonable difference, 5% difference, you say, okay, I'm pretty close to it, and use that value of C that gets you that those are equal, and use that to calculate your nominal capacity. And that is where I'm going